be careful.
Thank you very much, Richard. Go ahead.
So I was wondering how much relationship this has, or if you're aware of the relationship with the categorical natural language of people.
With the?
Categorical natural language processing people. So you have the categorical quantum mechanics people, and there's a sort of offshoot of them who realize similarly that you can phrase certain natural language problems in terms of, well, there's very similar logical constructions to you. I was wondering what overlap you saw.
No, this is a very important question. I know that there are these approach in the framework of category theorists, but unfortunately, both Roberto and I never studied seriously this approach.
Right.
Perhaps the serious limitation of ours, Roberto. Perhaps in the future, we should try to start to investigate possible comparisons between these two different approaches. So this a very good suggestion to us.
You are referring to the Oxford school, to the Oxford approach. I mean,
yeah, exactly. In terms of
Bob Cook and company, yeah.
Exactly. Yeah.
Right. You're right. Yeah.
I mean, in terms of so I'm in this area, and Bob used to be my master supervisor. So I feel comfortable saying I don't actually know that much category theory. One can get by with very minimum amount if you look at the diagrammatic stuff, and I think the natural language processing stuff is far friendlier than some. I can imagine if you look at the wrong part of that area, it is gobbledygook. However, if you focus on the natural language processing, you might see some serious similarities.
Yes, because they have, as far as I know, they have also very seriously studied the problem of contextuality in quantum mechanics. So the main concept that is common to quantum theory and to natural languages is just contextuality.
I do think you'll find a lot of overlaps having watched this presentation.
Yeah, because the approach is at the same time more abstract and more concrete than ours, because it's based on category theory and on diagrams, and it's a diagrammatical approach. But it's really very interesting. We should compare these two approaches. I think they have some strong similarities at first. Just as intuition. Yeah.
Okay, thank you for your answer.
Patrick, please.
Hello, can you hear me all right?
Yes.
Yeah. Yes, I don't see you, but I can hear you.
Oh, strange. Can anyone else?
It is the limitation of this program, in my opinion, because we should see the persons who are speaking.
Well, anyways, so thank you very much for both of your talks. I thought this was a really interesting program so far. Something I thought was interesting, so it seemed like the big motivation for this holistic semantics that you construct is that you want to avoid being dependent on this compositionality. So you want to avoid requiring kind of the truth valuation of atomic symbols, for instance, to fall down the path of just being composed in the usual manner, so that you can have more interesting quantum mechanical states and effects. Something I was wondering is if you've ever explored the possibility of doing that through some kind of modal semantics. So something like having some concrete truth values at the bottom level, and then having this holistic structure of something like your holistic state to provide you information about what the possible world structure and accessibility relations of that kind of semantics might look like. So the example that I have in mind would be if you have like a Bell state, two anti-correlated qubits, then you might have then you can have a truth valuation that gives those two atomic symbols true and false, and then false and true in two separate worlds. And then knowing the state would tell you that there's kind of an accessibility relation on that collection of worlds that would allow you to have this kind of possibility, such that in either world, it's possible that you're going to see either particle have either measurement outcome. However, that possibility is necessarily anti-correlated with the possibility of the other.
Yes, say something first, I and then you, Roberto.
Yeah, it's interesting. Your suggestion is quite interesting. You are not convincing, of course. You are trying to say that it is possible to give a Kripkean interpretation of the initial state of the Bell states in terms of possible words, isn't it? Mm-hmm. This is an interesting suggestion, I think, because it's because you see the possibility, potentiality, so to say, the fact that you have a compound system, a Bell state. Your idea is to interpret in a model way, as by means of a possible word semantics. So there is. This is a possibility. Yeah, it's interesting. Yeah. But we never thought about it. Yeah.
Oh, okay.
I would like to say something in this connection. Yes, I also agree that there are some natural connection between this kind of approach that belongs entirely to the quantum theoretic framework and a possible word approach. But very often, Roberto, we notice the following fact. The possible word semantics is very useful and has a lot of extremely interesting application. But there is a shortcoming, in our opinion. The shortcoming is the following, that this kind of semantics naturally creates a plurality of words. So it's ontologically very heavy. And from let us think of what happens in the case of the Kripkean semantics of modal logics, temporal logics, and so on. And in many cases, it is difficult to dominate this plurality of possible words from an intuitive point of view. Let us think, for instance, of the analysis of counterfactual conditionals in terms of possible words. In our opinion, a great advantage of the quantum theoretic formalism is the following, that you have a unique mathematical object, a vector that lives in a superposition state, that lives in a given space. And this vector, you can dominate from an epistemic point of view, this vector, because you know it mathematically. And this vector allows you to refer to a cloud of possibilities that are, in a sense, really potential. It is not necessary to think of possible word as a set of actual words in the sense of classical spell theory. So this is a feeling of mine. It's extremely interesting, extremely important, but it is very heavy from the ontological point of view. And the vector state formalism is useful from an epistemic point of view, because after all, we have access to these vectors. I don't know whether you agree about this factor.
I completely agree. Also,
no, you, Roberto, but Richard, I don't know whether Richard agrees.
No, Patrick.
No, just to add.
No, Patrick, excuse me, I don't see you.
Patrick.
For me, you are ghosts. No, ghosts speaking.
You have to interrupt the sharing of your screen, Marisa, to see Patrick.
So I will not refer to the past.
Yeah. Okay. Okay.
Okay. Now you can see Patrick.
Okay.
I didn't succeed in interrupting.
I would like also to add, Vincenzo, if I can, just a few words concerning this problem. You are right.
Yes, sure.
Because model relational semantics, also called Kripkean semantics, is classical, as Marisa said. So, in order to, because you have at the very background, you have classical logic. Then you had something, but the base is classically based. So you need this huge set of words just to take into account the notion of possibility. Here, you solve the problem at the very beginning, just because the clouds, as Marisa said, is intrinsically inside the state. You don't need to proliferate the states in order to take into account possibilities, because possibilities are just there. So it's a deep difference. And so Kripkean semantics is classical. This is the reason why, for example, Marisa and I think that, for example, epistemic logic, when we apply logics, if you want to have quantum epistemic logics, and you start from the Kripkean semantic for the S4, S5 system, I think you are wrong. Just because you try to force something that you have just there in a classical scheme. And so, and this is our starting point is different, is radically non-classical.
Thank you very much.